Congruency arithmetic, today's class will be done but with more number of problems, and the technique I am going to discuss with you today will be of great help to solve problems from Olympiad papers. After this session, you should start solving problems from Olympiad papers, including IOPM and RMO. I hope you will be able to do most of it. So let us start this session, which is actually a problem solving approach on congruences and Fermat's theorem. Before that, I'll tell you, those who have not attended the first session on congruency arithmetic and Fermat's theorem, this is actually part 2. I request you go through, if possible, after this session or later, but you must go through it, because all the concept I have explained there, although I am going to revise everything here again, but still we have solved some important problems, discussed some concept on congruencies and Fermat theorem in the last class. You must go through it. So let us start with this kind of problem where it is asked using Fermat theorem, show that a to the power p minus 1 by 2 is congruent with plus or minus, both plus or minus are there, plus or minus 1 mod p, where p is the odd prime and a is prime to p. Definitely I will tell you once what is Fermat's theorem. That is, when a is prime to p and p is a prime number, a to the power p minus 1 congruent with 1 mod p. Proof I am not given, because the proof you need the concept of circular permutation or binomial theorem or linear congruencies. We haven't done anything here, so I will not be giving you the proof, but once the concept of at least linear congruence is done, I will be giving you the proof, at least one proof. So a to the power p minus 1 congruent with 1 mod p, we have seen that for any integer a, or if you take the integer 10 say, and prime number you are taking 7, then 10 to the power 7 minus 1 is congruent with what? Think before I write here. 10 to the power 7 minus 1 congruent with 1 mod 7, that is 10 to the power 6 congruent with 1 mod 7. 10 to the power 6, when divided by 7, it leaves the remainder 1. This is the concept, isn't it? Now to prove that a to the power p minus 1 by 2 congruent with plus minus 1 mod p, where p is odd prime and a is prime to p, I will be using Fermat's theorem only, because a is prime to p and p is a prime number given. So from here we can write a to the power p minus 1 minus 1 congruent with 1 mod p. You go for simplification of this. This is not 1, because 1 we have taken on the left hand side, or added minus 1 on both sides. This is the property, you remember. I will be writing the property again. A congruent with b mod c. This implies that a minus b completely divisible by c. That's why this part is called remainder, no? So it has two meaning. Either you are dividing a by b, or I mean, you are dividing both a and b by c, they leave the same remainder, or when a minus b divided by c, the remainder is 0. This concept already I have explained. I am using that only. So this you factorize. You can write this as a to the power p minus 1 by 2 whole square, this minus 1 congruent with 0 mod p. So you go by this factorization, a square minus b square, a plus b, a minus b. So a to the power p minus 1 by 2 plus 1 into a to the power p minus 1 by 2 minus 1 is congruent with 0 mod p, isn't it? So this product is going to be equal to 0 mod p. So it means one of them is divisible by p. Both of them may not be, but one of them has to be divisible by p. So we can write, this implies that a to the power p minus 1 by 2 plus 1 is congruent with 0 mod p, or a to the power p minus 1 by 2 minus 1 congruent with 0 mod p. What does this imply? Take minus 1 on right side. This will be minus 1. What you are supposed to prove? This is equal to minus 1 mod p or plus 1 mod p. If transfer on right side, this is coming to be minus 1 mod p. And from the second one, if you do, it is going to be a to the power p minus 1 by 2 congruent with 1 mod p. So what is your concept here? A to the power p minus 1 by 2 divided by p will leave the remainder minus 1, or will leave the remainder plus 1. That's why you are writing a to the power p minus 1 by 2 congruent with plus minus 1 mod p. Let me explain this with example. This is true for any prime number, p, any prime number. So when you are going to prove that every square number is of the form 5q or 5q plus 1, this is a great help. Okay. So how to prove it? By using the, you can say, formula now only, or another version of Fermat's theorem, Fermat's little theorem. No, this you are doing Fermat's little theorem. So how to apply Fermat's little theorem concept to prove this? Every square number is of the form 5q or 5q plus 1. How to prove this? You start this manner. Let p equal to 5. You can take anything. Why I am taking 5? Because 5 minus 1 by 2 will give you the square. So you write a to the power 5 minus 1 by 2 congruent with plus minus 1 mod 5. This implies a to the power 4 minus 1 by 2, that is a to the power 2 congruent with plus minus 1 mod p, mod 5. So this implies what? That square is of the form plus minus 1 mod 5. So when a square divided by 5, the remainder is, this implies that when a square divided by 5, the remainder is either plus 1 or minus 1. If this minus 1 is not possible, you can normally we express remainder in the form of positive sign. So you write plus 1 or 4. But they have asked you to prove this thing, so I will be stick to this thing. Okay. So when a square divided by 5, the remainder is plus minus 1. Now if quotient BQ then we can write a square equal to 5q plus 1 or minus 1. Isn't it? Then why it is given this form? Because you don't know the number is multiple of 5 or not. Then automatically 5q will be there. So this we have proved, and this one already true. Why? Because you will be writing this manner. If the number is a multiple of, so I am proving this one, if the number is a multiple of 5, then A is already of the form 5q. You agree? If it is not, then it will be of the form, if it's number, then a square. A square is of the form 5q. Suppose you have taken, let me go back there. I am doing very fast. A is multiple of 5, that is, let A equal to 5k. This implies a square equal to 5k whole square, 25k square. So this implies a square can be written as 5q by taking q equal to 5k square. So square of integer, this you can write 5q because q is 5q square. So this implies that the square of any integer, if it is multiple of 5, it will be of the form 5q. If it is not, then it will be of the form 5q plus 1 or minus 1. This is one immediate application of Fermat's theorem, where we have derived this relation from Fermat's theorem directly. Now let us go for this one. Prove that 8th power of any integer of the form 17k or 17k plus 1. One similar sum I have chosen here. 1/8 power. Let a be the integer. Any integer is a. Its 8th power will be what? That we don't know. But two cases are there. Case 1 is what? Case 1, when a is a multiple of 18, multiple of 17. How can I write a? This implies a is of the form 17m, where m is an integer. So a to the power 18 in that case will be what? 17m to the power 8. So it is 17 into 17 to the power 7 m to the power 8. M I told you integer, so m to the power 8 integer, 17 to the power 17 also integer. We can write this product as k, 17k. Isn't it? What is the value of k over there? K is 17 to the power 17 into m to the power 8. Okay. So 8th power of an integer, if it is multiple of 17, can be put into this form 17k. But the other part 17k plus 1, why? Because that number may not be multiple of 17. You understand? The first case I have taken, it is 17m. But who told you that it will be of the multiple of 17 always? So we will go by case 2. Case 2 is what? Let a is not a multiple of 17. Let a is not a multiple of 17. If multiple of 17, it is done. Now we are going to prove let a is not multiple of 17. Fermat's theorem we have proved that for any integer a, this is congruent with 1 mod p. So put P equal to 17 here. What do you get? A to the power 8 congruent with, you put 17 better, no? Otherwise you might have a problem. A to the power 17 minus 1 by 2 equal to 1 mod 17. So this implies A to the power 8 congruent with 1 mod 17. So this implies that A to the power 8 minus 1 congruent with 0 mod 17. This implies that A to the power 8 minus 1 is going to be what? A to the power 8 minus 1 completely divisible by 17. So you can write plus minus 17. What you have got there? A to the power p minus 1 by 2 congruent with plus minus 1. So you write plus minus 1 here. Okay? A to the power 17 minus 1 by 2 plus minus. So you put plus minus over there. This plus minus 1 is 0 mod 17. So there it will be A to the power 18 will be of the form what? A to the power 18 will be of the form, A to the power 8 will be of the form 17k plus minus 1, isn't it? You write A to the power 8 plus minus 1 multiple of 17, you put 17k. Equality you use, so it is 17k. Now take plus minus 1 on right side, A to the power 8 going to be 17k plus minus 1. See the utility, so fast you can decide, and this is very important. 8th power proving by Euclid's lemma will take long time. Better you get it by Fermat's theorem whenever this kind of problem arises. Now, using Fermat's theorem, prove that 2 to the power 18 plus 9 to the power 18 is divided by 17. See how to prove this? We can use Fermat's theorem, we can use congruency only, but it is instructed to do it by Fermat's theorem. So let us do accordingly. 2 to the power 18, nearest prime number is what? 17. So let us approach with that, and 17 divisibility by 17 they have considered. So write 2 to the power 18 minus 1 congruent with, sorry, not 18 minus 1, 2 to the power 17 minus 1 congruent with 1 mod 17. So this implies 2 to the power 16 congruent with 1 mod 17. But we need 2 to the power 18. So what to do? We'll try it later. Let us approach with 9 to the power 18 first. The same manner, 9 to the power 17 minus 1 congruent with 1 mod 17. So 9 to the power 16 congruent with 1 mod 17. Hope you have understood. But we have to reach 18th power, isn't it? So you multiply here both sides by 2 square, 4. Isn't it? Here also you multiply by 2 square. So 9 to the power 16 into 2 square congruent with 1 mod 17. So this implies 2 to the power 18 congruent with 4 mod 17, and here 9 to the power 18 congruent with, I forgot to multiply by 2 square, 4 you must. So it is 4 mod 17. Check once. Oh, we need to multiply by 9 square, not by 2 square. So it is 9 square, that is 81. 81 mod 17. 81 mod 17 you can reduce further. You divide 81 by 17. How much? How much will be there? 17 4 ja 68. So it is 13 mod 17. So 9 to the power 18 is going to be congruent with 13 mod 17. Number 1 and this is number 2. So from 1 and 2, if you add two congruences, how, under what condition you can add? Told you last class, they have the same modulus. So you write 2 to the power 18 plus 9 to the power 18 congruent with 4 plus 13 mod 17. 17 mod 17 is what? What have you got then? You got 17 mod 17. So what is that? No remainder when 17 divided by 17. So it will be 0 mod 17 and your answer is there. 2 to the power 18 plus 9 to the power 18 when divided by 17, the remainder going to be equal to 0. Clear? Understood? See the application of Fermat's theorem, but in this world not all sums you need to use Fermat's theorem. Without Fermat's theorem also can be done. Okay? And by mixing Fermat's theorem and concept of ordinary congruency, like say A congruent with B mod M implies A to the power n for any positive integer, B to the power n mod M. This also helps. All problems are not solvable by using Fermat's theorem only. All problems are not solvable by congruency arithmetic only before Fermat's theorem. But some graded sums are there, can be solved by using combination of congruency and Fermat's theorem. Let's see this sum. How do you do 2 to the power 41 mod 23? It's up to you how do you do. But I am going to show you the easiest one. I think if you find easier method, definitely you will share with me in my WhatsApp or in the comment box. You write you have a better method. I have to reach, I have to walk a few lines, a few miles before I complete the sum. So definitely I will be waiting for a good solution from you. And I hope those who are attending the session, practicing sums with me with their pen and paper. Otherwise it is not of any use. Believe me, you can see it later, but whenever you see this session, you must sit with your pen and paper. Clear? Let us do it. Mod 23 is there. 23 is a prime number. Let us take that advantage first. Fermat's theorem. A to the power p minus 1 congruent with 1 mod p. So let p equal to 23. What happens then? 2 to the power 23 minus 1 congruent with 1 mod 23. 2 to the power 22 congruent with, but it is 2 to the power 41. How many steps ahead of this thing? It is 2 to the power 22 only. 1 mod 23. I need 2 to the power 19 more to multiply with this. But how can I? Think about easier method. So this is by Fermat's theorem. We have no, do we have any other way to use it? Yes, probably. But 23 we cannot get apart from this case. So that you have to do manually with the help of congruency only. Let us start with this simplest approach here, that 2 to the power 5, let us start with that. 2 to the power 5, simple idea of congruency, it is congruent with 7 mod 23. Agree or not? Because 2 to the power 5 is what? Is 32. 32 minus 7. No, not 7. It will be 9. Sorry for that. 23 minus 9 is 32 minus 9 is 23. So can be done. 22 to the power 5 is this thing. Does it help? Does it help? You start with 2 to the power 7. Take a bigger one. 2 to the power 7 congruent with what? 128 mod 23. This is congruent with, divide 128 by 23, 515, it's coming 8. You understand what I am doing? I have divided this mentally by 23 and wrote the remainder. So this implies that 2 to the power 7 whole square, should I take 2 to the power 5 I got. If I take 7 to the power 7 square, 14 and 5, their product will be 9. That's why I am approaching this way. So make square of two sides. Squaring 8 square mod 23. Therefore 2 to the power 14 congruent with 64 mod 23. If you divide by 23, 69, this is what? Check. 64, 56 are 8. This is coming 8 mod 23. So you got 2 to the power 14. This is, say, number 3. You got 2 to the power 5. 9 mod 23. This was our number 2. And check 2 to the 1 also. 2 to the power 22 congruent with 1 mod 23. Then what will you get? You multiply these three things. Multiplying, what will I get? So multiplying 2 to the power 14, 2 to the power 22 is 72 mod 23. Clear? 72 mod 23 is what? Divide by that. So it will be 3 mod 23. And left side what have you got? 19 and 22. 2 to the power 41 is congruent with 3 mod 23. So 3 is the remainder when you divide. Clear? I hope you have understood. So this was the sum where I have used Fermat's theorem mixed up with the concept of congruency. I hope you have practiced with me. Then only it will work. I'll tell you repeatedly. Try next one. 333 to the power 333 mod 7. Okay? Many ways are there. In IOQM, if you get this question, you can do it by using cyclic method. You can do it by using binomial theorem. But I'll tell you more elegant idea you get in number theory. In Fermat's little theorem, we can start directly with that. But 7 is the prime number, so you can answer, you can start this way. We have 333 to the power 7 minus 1 is congruent with one big step, because this is coming 333 to the power 6 congruent with 1 mod 7. Now you need what? 333 to the power 333. Raise the power to 55 because 330 will come directly. Isn't it? 6 into 55 if you do, it is 39. Wait. To the power 15. No, it is coming 330. I did it mentally. Yeah. So you raise the power to 55 on both sides. This to the power 55, 1 to the power 55 mod 7. So this implies what? This implies this is congruent with 1 mod 7. So we need more. 333 to the power 330. We need 333. 3 more are required. Then what to do? 3 more are required. What to do? You just go by this. You take number 1. Go by ordinary division. If you divide this by 7, then what is the remainder? What is the remainder? Just calculate it. 3 that you divide by 7, 28, 49. Yeah, it's coming 4 mod 7. Okay. So I need 333. I have 333 to the power 1. So raise the power to 3 on both sides. This will be congruent with 4q mod 7. Clear? 4q mod 7. Now you multiply these two relations. This is number 2 congruency here. So multiplying 1 by 2. What do I get? This into is congruent with 1 into 64. 64 mod 7. So this implies isn't it? So answer is this. This is congruent with 1 mod 7. When divided by 7, it will leave us the remainder 1. Clear? Hope you have understood. Go for next one. What is the remainder when this sum is divided by 4? Do you need Fermat's theorem? You think? Then I will help you. Before I do it here, you must think what to do. Is there any way? By Fermat's theorem, what do you think? 4 is not a prime number. So don't think about prime number. Not all sums in this world can be done by Fermat's theorem. Only prime number divisibility can be done with that. So go by normal congruence. You write 7 is congruent with minus 1 mod 4. Because why? 7 minus minus 1, 8. 8 is divided by 4. So 7 congruent with minus 1 mod 4. Therefore, 7 to the power 32. You raise the power to 32. And very interesting, because minus 1 to the power 32 is 1 only. So 7 to the power 32 congruent with 1 mod 4. We need 6 into that. Multiply by 6. 6 into 7 to the power 32 congruent with 6 mod 4. Clear? This is 1. And the next one, 9 to the power 45. 9 is what? It is congruent with 1 mod 4. Therefore, 9 to the power 45 congruent with 1 mod 4. Now multiply by 7 because you need a 7 over there. This will be congruent with 7 mod 4, isn't it? So the same thing can be written as, this same thing can be written as what? Because you can divide 7 by 4 once and 3 is the remainder. So it is 3 mod 4 and this is number 2. And here what have we got? 6 into 7 to the power 32, first term. Here what have we got? The second term. And they have the same modulus. They can be added. They can be multiplied also. Let us add. Let us add. Adding 1 and 2. What do I get? 6 into 7 to the power 32 plus, this is congruent with 6 plus 3 mod 4. This is 9 mod 4. This is 1 mod 4. Because if you divide 9 by 4, remainder is 1. So what have we got? What's the remainder? It's a huge sum. We got it by ordinary congruency, not by Fermat's theorem. Because 4 was not prime, we had nothing to do. And when this sum divided by 4, remainder is 1. Clear? Now get ready for solving the most interesting problem on Fermat's theorem I have discussed ever. Okay? Think about this sum. Before I do it here, you should try to do on your own. Prove that n to the power 11 by 11. 11 is what? Prime number. N cube by 3. 3 is what? Prime number. So possible to use Fermat's theorem. What they have asked you to prove? This sum is an integer for every integer n. Number theory is so powerful in algebra, no other topic can help you so fast. This same sum I'll show you in binomial theorem, but you need more steps over there. I'm not saying that binomial theorem you don't need number theories all. No, all are very powerful, but this time number theory more powerful than binomial. Okay, so let us try. N to the power 11 by 11. So let us see what we can get if we use Fermat's theorem. N to the power 11, n to the power 11 is congruent with 1 mod 11. So therefore, n to the power 11 minus 1 when divided by 11 leaves no remainder. So can't I write n to the power 11 minus 1 equal to 11 into an integer k1. K1 is an integer. K1 is a positive integer we are taking. Okay, do it for positive integer. Number theory is for positive integers. So k1 is positive integer. Initially we assume this. You got n to the power 11 now 11 k1 plus 1. Now n cube is what? This is congruent with 1 mod 3. The same manner we can write n cube equal to 11 k2 plus 1. Clear? Where k2 is another integer. K1, K2 both are integer. I am writing K1, K2 belongs to n, set of natural number. So now n to the power 11 by 11, n cube by 3, 19 n by 33 is what? Put the value of n to the power 11. 11 k1 plus 1 by 11. N cube is what? 11k2 plus 1 by 3 and 19n by 33 as before. Clear? Let's see what happens. Let's see what happens over there. Can you add all these? Can you add all these? Acha, one thing, this is n to the power 11 minus 1. No one commented on this. So this is basically going to be n to the power 10 minus 1 0. So you multiply by 11, multiply by n on both sides, then it is coming what? If you multiply both sides by n to the power 10 minus, you write minus 1 here, now multiply by n. So this is going to be n to the power 11 minus n, that is 11k1. So this is plus n over there. And here what you are getting? This will give you n square minus 1 equal to 0 mod 3 multiplied by n. So n cube will be 3k2, sorry, it is 3k2 and then plus n. Why? Because this relation you are multiplying by n. N cube minus n is congruent with, so from there we get n cube equal to 3k2 plus n. n to the power 11 is what? 11k1 plus n. So this is n, this is also n, and this is 3k2, not 11k2. Okay, so now you separate, you write 11k1 by 11 is k1 plus n by 11, k2 plus n by 3. k1, k2 belongs to n, so you write here k1 plus k2 plus, add these 3, 33, so 3n, 11n, 19n, k1 plus k2 integer plus 33n by 33n. So whole thing is going to be an integer. Isn't it? So you learn from my mistake. I did a wrong application here. It will be 11 minus 1, not 11. Be careful. Anyone can do mistake here. But some was not coming. That's why I have changed. That's why I have checked. And then I have corrected the step. Clear? Hope you have understood. Go for next one. Find the remainder when the sum is divided by 5. This is ordinary sum. But I have given you this sum to say that ordinary congruency also very powerful. If you write it in this manner, then from here to here, this sum is divisible by 5. Okay, so if somebody writing by using this congruency 100 factorial mod 5, then this is going to be, because this thing is divisible by 5, we will not take into consideration, we remove it, this thing mod 5. So this is what? Factorial for 24, 30, factorial 3, 6, 24, 6, 30, 32, 33. 33 mod 5 is what? 3. So remainder when you divide by 5 is equal to 3. Clear? This we need not use Fermat's theorem. Go for next one. Find the remainder when 1 to the power 5, 2 to the power 5, 4 to the power 5 up to 100 to the power 5 is divided by 4. How you proceed with this sum? Let us go step by step. You write here just the result of 1 to the power 5. You write few terms only. 1 to the power, why I said so? 1 to the power 5 is congruent with 1 mod 4. 2 to the power 5 is 32, 32 completely divisible by 4, so mod 4. For this kind of sum we need a pattern where it get cancelled. Some may be sum of 1, some may be 1 0 like that. So it is 0 mod 4. 3 to the power 5 is how much? You know, 3 congruent with minus 1 mod 4. So 3 to the power 5 congruent with minus 1 mod 4. So therefore, what? This will give us minus 1 mod 4. 4 to the power 5, 0 mod 4. 5 to the power 5, 1 mod 4. 6 to the power 5, check, 6 to the power 5 is nothing but 2 to the power 5, it is 0 mod 4 again. 7 to the power 5 is nothing but 3 to the power 5 mod 4, this will be again what? Minus 1 mod 4. And 8 to the power 5, 0 mod 4. So there is a cycle of 4 terms. If you add any 4 terms here, 1 to the power 5, when you add all these, it is coming 1 plus 0 minus 1 plus 0, 0 mod 4. Here also, this sum congruent with 0 mod 4. And how many blocks will you get here? 1 block, 2 blocks, 3 blocks, 25 group of terms are there. And every block is giving 0 mod 4. Every block is giving 0 mod 4. You agree or not? I have proved also. Sum of 4 terms you take, it will be 0 mod 4. Next also 0 mod 4, 0 mod 4, this way 25, all will give you 0 mod 4. So in this thing divisible by 4, remainder is 0. Go for next one. Just a minute, it is overlapped. Overlapping effect. How to prove this? N7 1 n to the power 12 minus 1 divisible by 7. It's very easy. Why? Can you see something there before I do? N to the power 7 minus 1 is congruent with 1 mod 7. This you could have done. 1 mod 7. So n to the power 6 to the power 2. So therefore, done. So what does this imply? N to the power 12 minus 1 congruent with 0 mod 7. Completely divisible by 0, completely divisible by 7. N to the power 12 minus 1. See how interesting is this? Any digit to the power 12 minus 1 divisible by 7. These are marvels of number theory. So many things are there in number theory to invent, to describe, you won't believe. Go for next one. Prove that a to the power 12 minus b to the power 12 is divisible by 91 when A and B are both prime to 91. We are going to apply this congruency if X congruent with Y mod Mi. This implies, it means X congruent with Y mod M1, X congruent with Y mod M2 mod Y mod M2 X congruent with this. I am telling you because we need the concept here. If it continues this way, then X is congruent with M1 into M2 into M3. Even you can write X congruent with Y, because divisible by this means divisible by their LCM also. LCM we are taking this manner. Okay, I am going to use this thing. Better to say with this only. See how to do it. Here you go by divisibility by 7 and 13, because 91 is a prime number. We look at that first, isn't it? So a to the power 13 minus 1 congruent with 1 mod 13. Clear? A to the power 13 minus 1 you got, a to the power 7 minus 1 will be what? This is also 1 mod 7. These two are prime numbers. We don't need, we just multiply here, no problem. Can we multiply it? A to the power 12, this concept we will need next one. Here too is just multiply ordinary. I thought I can take the help of it, but it's coming more easier way. That's why I am changing my mind. You got a to the power 6 minus 1, a to the power 7 minus 1. So you make square here. You can just multiply, or that one also equally applicable. So a to the power, it is simple logic. A to the power 12 minus 1 divisible by 13. A to the power 12 minus 1 divisible by 7. 7 and 13 prime. So from 1 and 2, what can I say? From 1 and 2, we can say that a to the power 12 minus 1 divisible by 7 into 13, 91. This is number 3. This is for any integer a. B is a similar integer. For b, what can I write? The same way. Similarly, 1 mod 91. So you just subtract now. Just subtract now. You are just going to subtract now. See what is happening there? If you just subtract a to the power 12 congruent with same modulo, no? So you can subtract 1 minus 1, 0 mod 91. Therefore, b to the power 12 is divisible by 91. Am I correct? Hope you have understood. Hope all of you have understood. Let us go for another very interesting sum. that prove that ABC into this thing is divisible by 11 for all integers A, B and C. How to prove it? ABC, A to the power 5 minus B to the power 5. Same manner for 3 integers. B to the power 5 minus C to the power 5, C to the power 5 minus A to the power 5 divisible by 11. How do you prove this? To prove this, we just consider case 1. When one of the, no, don't say one of the, when at least one of the digits is a multiple of 11. This implies that this is divisible by 11. You agree or not? When one of them divisible by 11, this product has to be divisible by 11, isn't it? But case 2 also there. When none of them is divisible by 11, then what do you get? You go by Fermat's theorem. A to the power 11 minus 1 congruent to 8, 1 mod 11, isn't it? A to the power 10 congruent to 8, and this we have seen before. A to the power p minus 1 by 2. Let us use that. A to the power 11 minus 1 by 2 congruent with what? Plus or minus 1 mod 11. So this gives us a to the power 5 congruent with plus 1 or minus 1 mod 11. So what does it mean? This implies that a to the power 5 when divided by 11 leaves remainder 1 or minus 1. Can I write minus 1? No. Because remainder always kept in the form of positive quantity. So we cannot write this. We don't have the right to write this. So what will I do? We write that is 1 or 10. You can add 11 over there. So when fifth power of a number divided by 11, it will keep remainder 1 or 10. So out of these products, 3 products you consider. This one, and similarly for b to the power 5, similarly for c to the power 5. So when you write a to the power 5 minus b to the power 5, then remainders will be what? Remainders will be 0, isn't it? Or what? You think this manner. A to the power 5 leaves remainder 1 or 10. B to the power 5 leaves remainder 1 or 10. B to the power 5 minus C to the power 5 leaves remainder 1 or 10. Their difference also. C to the power 5 minus C to the power 5 leaves the same remainder. So this part leaves remainder 1 or 10, isn't it? This implies 0 or 9, better to say, because when all are leaving 1, then 0. All are leaving 10, then 0. If it is not, it will be 9. Isn't it? So remainder will be, when you divide this by this, remainder will be 0 and 9, better to say. Here remainder is 0 and 9. Here remainder is 0 and 9. You understood this way? If you don't understand, just go by this. One of them leaves remainder 1 or 10 when divided by 11. So here it leaves remainder 1 or 10, leaves remainder 1 or 10. So at least two of them leaves remainder 1 or 10. A to the power 5 or b to the power 5 or c to the power 5, these three quantities, at least two of them have the same remainder. So it means their difference will be 0, at least in one case. You agree? So this product is always divisible by 11 for all integers a, b and c. With this sum, this session will be concluded, but you don't leave the habit of practicing sums. I will be sharing some more problem with you. You must do it. Thank you for staying with me.